A black hole is a region of space and time where gravity is so strong that nothing, no particles or even electromagnetic radiation, such as light, cannot escape from it. The theory of general relativity predicts that a sufficiently compact mass can deform space and time to form a black hole. The boundary of no escape is called the event horizon. Although it has an enormous effect on the fate and circumstances of an object crossing it, according to general relativity, it has no locally detectable features. In many ways, a black hole acts like an ideal black body, as it reflects no light. Moreover, quantum field theory in curved spacetime predicts that event horizons emit Hawking radiation, with the same spectrum as a black body of a temperature inversely proportional to its mass. This temperature is on the order of billions of a Kelvin for black holes of stellar mass, making it essentially impossible to observe directly. What's going on, guys? I'm back again. It's been a long since I came up with a new topic, hope you didn't forget me. Anyways, so today we are gonna discuss about our own black hole that exists in the Milky Way galaxy. So tighten up your sits and get ready for some Did You Know? Sagittarius A star is a bright and very compact astronomical radio source at the galactic center of the Milky Way. It is located near the border of the constellations Sagittarius and Scorpius, about 5.6 degrees south of the ecliptic. Sagittarius A star is the location of a supermassive black hole, similar to those at the centers of most, if not all, spiral and elliptical galaxies. Observations have several stars orbiting Sagittarius A star, particularly star S2, have been used to determine the mass and upper limits on the radius of the object. Based on mass and increasingly precise radius limits, astronomers have concluded that Sagittarius A star is the Milky Way's central supermassive black hole. Reinhard Genzel and Andrea Ghez were awarded the 2020 Nobel Prize in Physics for their discovery that Sagittarius A star is a supermassive compact object, for which a black hole is the only currently known explanation. Astronomers have been unable to observe Sagittarius A star in the optical spectrum because of the effect of 25 magnitudes of extinction by dust and gas between the source and Earth. Several teams of researchers have attempted to image Sagittarius A star in the radio spectrum using Very Long Baseline Interferometry, VLBI. The current highest resolution, approximately 30 as measurement, made at a wavelength of 1.3 mm, indicated an overall angular size for the source of 50 as. At a distance of 26,000 light-years, this yields a diameter of 60 million kilometers. For comparison, Earth is 150 million kilometers from the Sun, and Mercury is 46 million kilometers from the Sun at perihelion. The proper motion of Sagittarius A star is approximately 2.70 miles per year for the right ascension and 5.6 miles per year for the declination. There are a number of stars in close orbit around Sagittarius A star, which are collectively known as S-stars in various catalogs. These stars are observed primarily in K-band infrared wavelengths, as interstellar dust drastically limits visibility in visible wavelengths. This is a rapidly changing field. In 2011, the orbits of the most prominent stars unknown were plotted in the diagram at right, showing a comparison between their orbits and various orbits in the solar system. Since then, S62 and S4714 have been found to approach even more closely than those stars. Neither wormholes or black holes have actually ever been seen directly, even with the sophisticated equipment in use today, but both follow inevitably from Albert Einstein's general theory of relativity, and plenty of indirect evidence has been obtained, at least for black holes. The ideas have certainly been more than readily accepted by the science fiction community, for whom they suggest intriguing possibilities. One of the most famous black hole theorists, the British physicist Stephen Hawking, proposed the 4 laws of black hole mechanics back in the 1960s, and calculated in 1974 that black holes should thermally create and emit subatomic particles, known today as Hawking radiation, until they eventually exhaust their energy and evaporate. Yet, as recently as 2004, he admitted to losing a bet he made with the Caltech physicist Kip Thorne and John Preskill, and overturned his long-held belief that any information crossing the event horizon of a black hole is lost to our universe, and is now convinced that black holes will eventually transmit, albeit in a garbled form as we perceive it in our observable universe, information about all matter they swallow. Information in this sense may be loosely defined as that which can distinguish one thing from another, and essentially refers to the identity of a thing and all of its properties. This is a good indication that the theory is far from cut and dried, and research, both theory and observation, into this challenging area proceeds unabated. As an example of the complexity of the subject matter, a short quote from Professor Hawking's 2004 presentation may suffice. The Euclidean path integral over all topologically trivial metrics can be done by time slicing, and so is unitary when analytically continued to the Lorentzian. Now, I hope that you like this video. If you do, don't forget to like and subscribe to my channel. Also tap on the notification bell so you can get my videos at first. See you all again, with some more facts that will amaze you totally, and after which, you would ask everyone, did you know?